Hi guys, and welcome to our updated as of 2004 edits to relationship extraction. So we've taught this section a couple times and we have some new and cool ways to use Snorkel, especially to do relationship extraction, but also through dependency parsing. So let's get started. In this section, we're mostly going to talk about distant supervision techniques. So this is a way that you can build your own labeled data set using rules and regular expressions and Snorkel to then potentially take that data set and just use it as data, or to use it for a training data set for future machine learning pipelines. Okay? So we could use dependency parsing to build those data sets, and I'll show you how. Or we can use what's called the Snorkel package to apply those parsing techniques. So we can actually use Snorkel for a couple of different ways. So this really should say dependency parsing for that building, or using named entity recognition to then process with Snorkel. Okay. So Snorkel has a really great demonstration on their website using spouses, but it's very specific and they have a lot of special functions. So we've really written this section to sort of grab it and show you the pieces one piece at a time. Okay. So what we're going to do is we're going to create a data set, and we'll show you an example of creating a data set using dependency parsing. And then we'll create an example of a data set using named entity recognition. From this, we'll add labels to that data set using Snorkel how to do that component, and a much smaller kind of tame example of Snorkel. So it is much more powerful than we're showing you, but we're getting you started on how it is a labeling package assistant. Okay? And so I could then stop and analyze those relationships, or I could use that new labeled data set for training purposes. So you want to kind of go through this process a couple of times until you've found all the labels you're looking for, and you've sort of managed to put together a valid training data set. And then you could use it to build your own machine learning pipeline. But given that the code that we're building also would run on new data, you could use that pipeline to find new data to continue building labeled data sets. The advantage to the machine learning version is that it might infer from your text things that you hadn't thought of. So you might test both to see which one is better. Do I continue to use the hand-built pipeline, or do I train a model and use that model from then on out? Okay, so it's kind of a way to sort of get yourself started with relationship extraction, because these data sets are not as plentiful as things like part of speech tagging or sentiment. There's like 8,000 sentiment data sets that work pretty well. Relationship extraction is one of the hardest tasks in NLP, just simply because it is so context specific. So at the beginning of these lectures, we talked about how named entity recognition and information extraction is very difficult because the models are very brittle, meaning that they break quite frequently and they don't generalize to new contexts. Whereas sentiment analysis, pretty consistent, will work on many contexts. So let's look at how we can build our own data sets if we don't have a training data set. Right. Then the last component to this that'll really help us see what we've learned is visualizing the data. So to do that, we are going to show you both. How do I visualize the data that's raw? So just the raw, like all of the links that we found in the text. Or once I've got it labeled, how can I break that down by label to help me visualize? And these things are called knowledge graphs, and that allows us to display and or show off relationships. So knowledge graphs is just a fancy word for a network graph picture. And so it's the one with all the bubbles and the connections between them. The real problem that you're going to have when creating these, especially at the beginning, is that there'll be just too much stuff on the graph. So we'll talk about when and where you need to kind of pare it down. Because if you have a text with a lot of entities in it, you'll get a lot, you can't read it. It's just got too much going on. Okay. Now, the Networkx package that we'll use does have some issues with earlier versions of Python. So if you're only on like Python 3.7, I want to say, you may have to kind of downgrade NetworkX to work with certain versions of different packages, just as an aside. As you get to the more advanced packages, like being able to upgrade, I think it's textacy and NetworkX, and it'll stop having these problems. So it's something they fixed in later versions of Python, but some of these earlier versions can't run them. So upgrade your Python as well. What else? And last point on this slide, the NetworkX, I am either not the greatest at it, but it's not the best visualization tool in the sense that there are other packages that have more control over the bubbles themselves. So one thing you can do is export the data and use a free set of software like Cytoscape is a really good one, and Gephi. So those are both standalone pieces of software that are open source that really allow you to make the cool pictures that you see in the text. All right, so let's tackle it now then. Okay. So first, just to show you what dependency parsing looks like on our information about the chief executive for Microsoft here. And so we can use Spacy's NLP function, right? The one we pre-built. So remember, this is 2 lectures ago now, but there is an NLP function, which is the one that we've loaded from Spacy. So we loaded the English language model, we called it NLP, okay. And we told it to do dependency parsing. Okay. So what it returns for you is a tuple of information. The first one is the token that it's looking at. The second one is the token that it's linked to. And the third one is the information about what type of dependency it is. So in dependency parsing, there's all these different tags that we can use to tell it what it depends on. And most of the focus is on the verb in the sentence. But here it's telling us this is a compound. So it's figured out that these first 3 words are a compound. Okay? And it's tagged the last word as the subject of the sentence. Sentence subjects are often really important when it comes to relationship extraction because they're the ones doing the action. Okay? So the in subject is something we're going to look for because they're the ones being acted upon or doing the action in the sentence. You'll notice here that the word is the root because dependency parsing focus heavily on verbs. So that is the action that's happening. So we have our subject of the sentence who is doing or is having the action done to them if it's in a weird English tense, right? Then we have the action itself. What's the verb? And then there's something else we can look for here, which is the direct object. Okay, so the direct object is the thing being acted upon. So if I said, he gave me a ball, okay, he is the actor, the direct object would be me, the thing that's being acted upon. And the indirect object in that sentence is considered the thing that he gave me, right? Which is a ball. It's what the direct object is sort of having an action with, so to speak. So there are 3 principal pieces that we're kind of going to look for. So the subject of the sentence, if there's a direct object in the sentence, and if there's an indirect object in the sentence. Okay. And the way we're going to do that is grab in subject from our tags. And then we've got some other ones. There's P object. Okay. And then which is, I think in their terms, participle object, which we'll use. So anything ending in object. And then there's one called D object. Here we go. D object. Okay. So we're going to grab those 3 from our dependency parsing and use them to help us label for relationship extraction. Now quickly, let me show you a visualization of this because this spacy is a really cool function that's part of spacy that allows you to make a nice visualization of the sentences that you're interested in. And we might be able to see just a little bit better here. So is our root word here. We've got our in subject. Now the current code that I've helped write does not grab these compound pieces quite yet, but it could be modified. So we're going to grab our in subject. We could also potentially be interested in our adjective. Ooh, Let me have a little more coffee. Hmm. Adjective modifiers, right? Because that would tell us something about the subject. But here we're going to look only for objects because of the relationship extraction. We're not trying to um, define the subject. We're trying to look for things the subject is related to. So we've got P object here, which is officer in this sentence. Preposition, blah, 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 blah. Another P object here, Microsoft. Okay. Direct object is the person's name here. So we're going to grab those types of things because that would tell us the sort of who and here the when of what's going on in the sentence. But it's a really cool, nice graph. They have another option. Scroll back over here, where you can tell it to display the entities, and that's what we're going to move to next. Okay, and the entities in this one, not as great. It decided that the person's first name was a geopolitical entity, which is not, it's, right, but this has become a person. Um, it gives you nationalities, that kind of stuff, organizations, people, dates. I like that it just deleted the date. So it's not a perfect picture, but it can kind of show you like what it's grabbing from the sentence. So we're going to take both approaches to relationship extraction and see if they give us different answers. All right, now let's try it. So what I'm doing in this example is I have one of my favorite podcasts that I've listened to a couple times is a series. It's called Lovecraft Investigations. It is a kind of a modern take on several of H.P. Lovecraft's famous stories. It's super fun if you like podcasts, kind of horror-inspired podcasts. So what I have is one of their episodes, just one, because otherwise this takes forever. This is a slow process, and you'll see why. One of their episodes where we are going to investigate all of the dependencies and the entities and see if we can see how they're linked to each other. Okay. Now, we'll say that formal text works much better for these types of analyses than sort of informal talking, but formal text is really boring as an example. So you'll see what I mean here in a little bit. Okay. So here's the first sentence. Sir Godfrey Tillinghast, Mr. Haywood, allow me to present Dr. Jonathan Willett. So we get several names in one sentence. Okay. So for named entity recognition and dependency parsing, we need to work at the sentence level. So one thing we can do is take our data frame of data and break it down by chunks, but it will target this at the sentence level. Okay. I have it where it's like one line of speaking per line, but you could also take in one giant, huge piece of text and break down where each sentence is its own row in a pandas data frame. Okay. Go back to the processing lecture if you need help remembering how to do that. So I've imported pandas. I've made it one spoken line per row in this data set. And then now you can see I have this in a nice formatted data frame. Okay. This data is already clean, so I don't need to do a whole lot to it. But as a reminder, for named entity recognition and dependency parsing, you don't do a whole lot to the data set. You don't want to remove punctuation. That's a very important clue in the data set. You don't want to lowercase because uppercasing is a very important clue in the data set. So mainly we just want to make sure there isn't any garbage in it and take those things out using regular expressions, for example, because emails and usernames are probably what you're looking for. So very little processing here, maybe breaking it into sentences to get yourself started, and then maybe just doing a little bit of cleaning here and there. Okay, so not a whole lot of processing. A lot of that processing stuff will happen in the next videos where you'll go over classification techniques. That requires a lot of cleaning. Now the /ins here mark the end of a new line return in my data set. Those are not going to cause me any trouble, so I'm not going to take them out because they don't really mess up what I'm doing. Great. All right, this is a giant function that I wrote for my class several years ago, and I want to walk through each piece kind of one at a time to show you what it's doing. And what it is it's a combination of things that we've learned to really pull everything out. And so instead of doing this one step at a time, like, okay, do this, then this, then this, and now on the next row, what we're going to do is write this function as a way of applying this to several data frames. Okay, so this is specifically for dependency parsing. We have another one specifically for entity recognition, but they're almost identical. You probably could put both of these functions together and make it a little more flexible, but I thought that might be confusing for folks, so I kept them separate. Okay, so I'm going to switch over here to RStudio because I can make the text a little bit bigger, and I can also show you one line at a time what is happening. Okay. All right, so you need iter-tools and their combinations function here. What combinations does is it takes every two-way combination in the data set. Well, it actually could do more, but we're setting it up to do every two combinations and pair them together. So clear this out. Oh, it won't let me. It doesn't like my keyboard. There we go. Cool. So we're writing our function, get dependencies. Okay, let's make our text this first line of this sentence so that we can see what's happening here. Come on. Oh, are you not going to let me copy? There we go. Copy. Try again. I'm going to say text equals, I'm going to move my face so that it's not in the way. There we go. Perfect. Oh, no, sir. It does not like that. Try that again. Why is Python so picky? So picky. That should work. Right. So here's our text, our line of code here. So if it's good, it should pull all three names from this text. We're going to run one line here, processed equals NLP. Okay, so what is our processed function? Well, it doesn't look like much because spacy will return the original sentence, but there's a whole lot in here that it has saved, right? So we can see like, oh, look at all this stuff that we can do with it. What do we want? Well, the first thing we want is to get all of the words back. So we're going to get a list of tokens from the sentence. Okay, hold on to that thought. It's going to come back later. Right now, we're just going to grab that list of tokens and we're going to use it several times. Okay, so let's run this sentence, this line, rather. Okay. So as you can see, now I have a list of tokens. Okay, this is just like our processing for part of speech tagging. First thing you got to do is figure out where the tokens are. We don't really care that the names have been broken into several pieces because this is just grabbing the tokens. Entity recognition will often put them together because it'll look at the whole text. If it doesn't, there's some other things you can do with spacy to fix that. Now here's what we're going to do. We're going to take the token and the dependency. So this is a little tuple, and I've forced it into a string a lot of different times within spacy. If you tell it to return the text or just the token itself, it'll return a spacy object, and that will screw up counting things and doing a lot of things. Every semester, this is the problem I have when I'm working a live example in class. I always forget this, so I made sure it was in the notes. So return it as a string, so it's not a spacy object, just in case. Now I want to return the token, just like here, dot text, right? The dependency for that token, this is the label that it gets for each token in my sentence, if that dependency is a P object, a D object, or a subject. If you decide you want to do adjectives and adverbs, you could add them to this. So this is a list that you could change. If you decide, no, I actually want those adjectives, I want those adverbs, you would add them right here. Okay, it's a mod and ADV for ADV mod. And then it might be RB mod for adverbs. You'd have to look at the list for dependency parsing. Okay, this is not the same thing as part of speech tagging, okay, where it's ADJ and RB for adjective and adverb. But you can find them by just running an example like we did up here. Okay. Spacy also has a nice list of what they are. So let's see what it found in our sentence. Okay, so I'm going to print out temp here. Geez, not enough copy. There we go. So it found several things in the sentence, not quite maybe what we were interested in, but still useful. Okay, so it'll return a list of tuples. Okay. First tuple is me. Allow me. So me is the direct object in the sentence, okay? Which it decided was the subject, but Mr. Haywood, allow me, actually technically should be the direct object, but that's okay. To present, so to present being another object in the sentence, indicating another object in the sentence, Dr. Jonathan Willett is our last name. So one problem that you'll have with the dependency parsing approach is that you'll only probably get the last name of a compound phrase, for example. There are ways to fix that, but let's just learn how to do the labeling today. So we've only got two of them, so this doesn't quite show you the best example, but what it will do in our next piece here is make all the two-way combinations. So if our temp, so I'm gonna show you what it does if there's more than two. Okay, so I'm just gonna make temp 2, 1, 2, 3, 4 here. When you use combinations, because I think that is a key component here. So to summarize, we've extracted our NLP, we've processed our tokens, so we get all of our tokens back. We've grabbed the entities, I'm sorry, dependencies, not yet entities. We've grabbed the dependencies for each one. If they are these types of dependencies, now what? Well, you can't have a relationship if there's one object in the sentence. Okay, relationship extraction requires at least two objects, because otherwise, what are you relating it to? Therefore, if temp is only one item long, it moves on. Like it skips all of the rest of this set of steps. Okay? This only moves on if you have more than one item. So we're going to make combinations. So let me show you what the combinations function does. Okay. It creates you a list of tuples. Okay, well, I made it a list. Creates you a set of tuples of every pair of combinations. Okay, one direction, meaning it won't give you 1, 2, and then 2, 1. Okay, so it only kind of goes forward. So 1, 2, 3, 4, I get 1 to 2, 1 to 3, 1 to 4. Okay, so every unique pair of combinations. Perfecto, because in relationship extraction, it doesn't quite matter if it's first or second. You'll get the same, it should give you the same label either way. And then once you graph it, it will sort of add them together if it's 1 to 2 or 2 to 1. More copy to help with the Python thinking. All right, so this is how it's going to work. But in our case here, running it on our data set, we only end up with one pair. Oops. Oh, no. Yeah, one pair because we only have those two. So if we have more than one, it would make multiple pairs. Now this next section, which runs, as you can see, the little orange line here. I figured out how to do this in RStudio lately, and it's been my new favorite thing. This little orange line here runs the entire section. Okay. So for every object 1 and object 2 combination. So here's object 1, here's object 2. So this is technically a list of tuples of tuples. Okay, so it's a list of tuples. So here's the tuple, the whole tuple pairs. I don't know why it's giving you the thumbs up, but it is. And then within that tuple are two tuples. Okay? And it should always have this structure where every big tuple is two little mini tuples with two items in it. Cool beans. So what we want to do is I'm going to call this object 1 and object 2. Since this is a function, it doesn't quite work to just kind of run this because you can't see what's happening. So I'm going to create these real quick. So we'll say object 1 is the first item. Oh gosh, what is this called? Temp 2. It's the first item, first pair. So let's make sure that looks right. Okay, so it's going to run that one. And then object 2 is the first item, the second pair. And so this loop will create that for you naturally. But since I'm showing you how this works, I have to kind of manually do it. Okay. So we're going to find the word in dependency one. So if it actually pulls apart several words, this allows you to grab just like the one word you need. For dependency parsing, you don't need this quite so much, but you do for entity recognition, and it doesn't hurt you for dependency parsing. So we'll let it work here. So object one's words is just the word me. This is the fun line. I love enumerate, but I couldn't quite tell you always what it does. So object one IDs here. It enumerate counts. That's what it does. So for each word in our object one words, okay, count what token it is. Okay, so counting upwards, value in enumerate tokens. Okay, I think I can just run this. Oh, it won't print it. Can I do? Probably not. Nah, it doesn't like it. But anyways, okay. So counting up one for one. Oh, I might be able to do I for I and enumerate tokens. Nope, still doesn't love me. All right. So counting upwards, 0, 1, 2, 3, 4. Give me the value in our enumerate tokens where token 0 is labeled token 0. I don't want the actual word. I want the number for the word if that value is in the object words. Okay, so it's basically taking our tokens list and saying, where the heck is object one word, which we saw was me. And so it goes, okay, 1, not it. 0, I'm sorry, 0, not it. 1, not it. 2, not it. 3, 4, 5, 6, 7. Hey, that's the right word. Moving on. So if we look at object one words, what we end up back with is me, and that should be the object one IDs, which is 7. Okay. And the point of this is if you have multiple words, so if you go back and fix your dependency parsing where these all come together as one word, one chunk, right? As one grouping, then let's say we had the whole thing, well, not me, but let's say we had Sir Godfrey Tillinghast as one dependency noun subject. Okay. Well, that's 3 words. So I got to figure out where it starts and where it ends because we're counting here. So it will tell me where each word is. It says if the length of object one words is more than one word, then grab the IDs of where the word starts and ends. But since our object one words is only one word, it'll say, here's the ID. So the ID is 7. And our object one IDs 2 is a tuple of the start and stop. Okay. So the goal here is to find where that object is in your tokens, figure out where it starts and where it stops. Okay. For reasons we'll get to in a few minutes. So trust me here on this one. So figure out where does it start, where does it stop. So I have this huge list here. If I was looking for Sir Godfrey Tillinghast, it starts at 0 and ends at 2. And that's what we want. If I'm looking for the word me, it starts at token 7 and it ends at token 7 because it's only one word. Now, this section does the exact same thing, but now only for object 2. Because we've got pairs, right? And so we need to know where it is. Object 2 words. There might be, yeah, this should not be there. There we go, updated. I don't think it'll affect our example, but we'll fix it. Okay, so 12. If it's more than 1, find it. If it's less than 1, grab it. So if I run this thing, oh my goodness. Python does not like you sometimes running if else's one line at a time in R. This is a very specific R thing. Otherwise, it runs fine when you run the whole big, huge chunk. I hate it. I can't figure out how to make it stop. So let's just run this. So we've got object 2 IDs. Oops, spelling is Still hard for me. There we go. Now, what do I do with all that? Take all that information, toss it into a empty list that we created. Okay. So we're going to create this list of lists where we have the original text that we put into it, the tokens, object one, just the word for object one, object two, just the word. Now, could you also extract the type of dependency? Of course, but we don't quite want that for our example today. Where does it start? Where does it stop? Okay. So what we'll end up with is this giant, super cool data frame that has all of the starts and stops. Okay. So let's look at this thing using RStudio because when you print it out in Quarto, it doesn't look great. Okay. So we have the original sentence. Okay. The tokens for that sentence. Now I am looking at this. If you're using Jupyter, you'll get this as a much better view. But since I'm looking at this in R, it's like interpolating what R should look like. But this is a list of tokens. Right? So it doesn't quite look okay in R, but anyway, so we've got our object one and our object two. Now notice here that all of our objects are going to be singular in dependency parsing. This is where named entity recognition will probably be a bit better for us, but we'll see. And sometimes they're not quite what you want, right? So we've got some dates, that's okay, but we've got a lot of words that are maybe not super great. Okay, so there are filters that we could do here. We've got the start and the stop for each one of those words. Okay, list. And we're going to use all of that to now add some labels to the data. Not quite yet, but that's really what these two columns are not necessary unless you want to add the labels. You could just use object one and object two to make the picture, which is what we'll do in a second. Now, back to the slides. Okay, so that's what all this huge function does. Okay, this is the pretty slide version. Now we've got the exact same function for NER, but let me show you the differences. Okay, the biggest difference is here. Get all the entities. So now we're taking the entity and its label for every entity as long as the label isn't blank. You could decide here that you only want person, GP, org. So you could change this here to be whatever list of entity types you're interested in. I always tell folks to start with everything and then whittle it down because not all entities get labeled correctly. So there might be some that you want that you're just not getting by looking at the text because they aren't being labeled correctly. Okay. Then all of the rest of this is very similar. I am storing this in stored entities. Could we combine these functions? Yeah, probably, and do a like sort of if else. But I think for our purposes, it was kind of nice to keep them separate, just so that you could see those differences without adding that extra layer of sort of if else complexity. So I called this one get entities, and it should work across all texts. This being the key difference between the two is this line, and then how I'm storing them. Okay, could just call it stored objects and use the name for both of them. No particular reason, I just kept them straight so that I wouldn't forget what I was doing. So let's look at what the entities look like. See how it's different. Okay, so we've got 15,000 pairs. Good gravy. That's quite a lot. We'll see how many did we get for the other one. 15,000 pairs. That's kind of interesting. I don't know that I expected to get the exact same number of pairs, but okay. Cool. And we should get more than one word. Now, this one doesn't seem that it got, let's kind of quick scroll. I don't see any that got more than one word. That's kind of interesting. But in a good entity detection situation, it will give you any time that there is more than one word. Okay. And I would say a lot of these entities are not super great. Let's make sure. Store. Oh. Well, no wonder there's a typo in my code. Let's try that again. No wonder it didn't work quite right. Right. We made a data frame of the last information. Ways to check your code. All right, let's run this again. All right, we got 683. That makes a lot more sense versus 15,000. So you're going to get a lot more stuff in the dependency parsing. I can't believe I didn't notice this when I wrote this code, but good catch. Live and in color. And now see how we have things that are like much more chunks of information. And so this will grab where the chunks start and stop. Okay. Much better. Okay. But you do get stuff that's kind of weird in the middle of, that's probably a date, right? And the code isn't super perfect sometimes at grabbing weird sentences like this. Kind of just depends on what's happening. Um, so, it will grab the start and stop, but sometimes it'll only grab um, two of the start and stops, but it's good enough to kind of get you going. All right, now none of my graphs are going to make any sense. So here's what we're going to do. We're going to hit render while I talk and let it re-render the notes because otherwise the graphs are going to not look right since I had a typo in my code. Okay, so we've applied our NER function. Now, to visualize those dependencies while the code reruns before we look at the pictures, what we need is a data frame that has the dependencies or the entities, either way, where they are in a format where it says, here's object one, here's object two, and here's the frequencies of those objects. Okay. And so it's kind of a conditional frequency table. But what you've done before with part of speech tagging is made like objects and then part of speech tag. And you can look like one of the example things to do from this set of lectures is to create a list of how many times each word is tagged as different parts of speech. Right, that's kind of a conditional frequency table. Same idea here, but we need a long format, which means we have each row is a pair of objects and their frequency. So instead of having a nice table like this, we want it to be like this. So the first thing I'm going to do is I'm going to exclude every time object one and object two are the same. Because if you use the same name or the same dependency twice, it will treat them as different pieces. So we're going to exclude every time those two things are equal. Okay? Because the object related to itself is not really a very interesting question. Also, the object related to itself will break a knowledge graph. So it kind of makes it a circular. So it's like, here's the object. It's the same object, and it's trying to draw a line between the bubbles, and it doesn't like that very much. So let's see. I think we were here. Great. And so what we'll do is we'll create what's called a co-occurrence table. Okay. Now this code is actually kind of like using PySpark. It's a way that it works in pandas as well. And so this kind of code just allows you to stack it on multiple lines. So we say, okay, take object one and object two in our bigger data frame. Okay. Group them together by object one and object two. Count. Okay, and reset the name of that count as frequency just for useful purposes. Okay. So our 15,000 rows turned into 6,000 different pairwise combinations and their frequencies. That's a lot. That would draw you a crap ton of bubbles and a ton of lines. So that's going to try to render 6,500 lines. Okay, it's not 6,500 bubbles because obviously 1963 is the same bubble on our network graph, but that's probably too much information. So on the next slide here, what I'm doing is filtering that down. Okay. The one problem that I see my students do is because they're copying and pasting code. Great, wonderful. That's what I'm hoping you'll do. I didn't write this all for fun. But be sure you actually look at your data frame to figure out what the lower number should be. Okay, so let's go back over here now that we have updated code. Run this bad boy again. So let's view that data frame. What? Not defined. literally just ran this. Okay, try again. Oh, probably because I spelled it wrong, right? Okay. So now I can kind of flip through. So I've got some very frequent items up here, lots of infrequent items down here. Okay. So I might start at 10 and just see what that gets me. Can we filter in Python? Does it work today? Ooh. Sometimes this doesn't work. Like you can tell it just got mad. There we go. So that'll give me 52. That's a much more manageable number, although it's being weird. Oh, it gave me up to 10. Whoops, wrong way. So I want to do 10 to, this is easier in Jupyter for sure. Why are you hating on me? Okay, it's hating on me, but whatever. So we could say, okay, that's going to be about 170. That's not terrible. Okay, so you want to filter it down, but one thing you can do is run this code over and over again until you find the right filter. So let's say I started with 5. I'm just gonna run this real quick. Make the picture. Whoa, too many bubbles. Okay, you can't read this. You can't interpret this. Too many bubbles. So let's back up and let's try 10. So you can run this a couple times. If you decide to go back down, you do have to rerun your data frame. I stopped here at 10, but that might still be too many, so I could do maybe 20. Until I got down to a manageable number of bubbles that I can interpret. Well, let's go back. Let's talk about the code. So this is the code that just sort of filters the data frame down. This is our graphing code from Networkx. Okay, so here's Networkx. You also need to load matplotlib because Networkx relies on matplotlib. So make myself a graph from what's called an edge list. An edge list is the data frame we just made. Object 1, object 2, frequency. That's all it wants. Okay. So I say, okay, here's the columns. We're going to call frequency weight because that's actually what it should be called in this data frame. So we could go back and save ourselves from trouble here by calling it weight from the beginning. Our source is object 1, so draw a line from this bubble to that bubble. Okay, so second one is object 2, and include the edge attributes. At the moment, we don't have any really of those except the frequency itself. Okay. There are different layouts, but this is my favorite one. Okay, and weight them by the weight. Okay. All of this is changeable. Okay, so I made the figure really large. It does not display in Quarto very well, but I made it really big so that it displays nicely one in Jupyter. It might be too big in Jupyter, so make it smaller. This is inches, so make it smaller. So you can tweak these numbers based on which software you are, or which IDE you are using to build this. Okay. Draw that graph, draw those positions. POS here stands for position. Make the nodes a specific size. Bigger is bigger. Make them sky blue for fun. Alpha is how transparent they are with the labels. Yes, you want the words on there. Font size for the words, and add a title. Okay. Now this piece here will not draw the lines between them. So to add the lines, we say, okay, for node 1, node 2 in the data, draw the lines. The edges here are the lines between them. And so it draws them based on, we can change the color here and it's alpha. Now notice that I commented this out. Okay. If all of your weights are very high, because in our data set, by filtering, all of our weights are really strong, it can make it very difficult to read because the weight lines get bigger and bigger. So instead, what you want is to just make them all a small width. So either one is appropriate, but you'll find as you play with these graphs that some of them are more readable than others. So here's our 21, and we can try it to show you. Code here a little bit. Oh, I know you're mad. Double indent. Grumpy Python. See? Unreadable. Because all of them are fairly strong and one of them is really strong. So the point of this is to be able to see those strengths, and there are probably some different ways that you can kind of play with this, like make them different colors or something, but at the moment that is not readable, so I turned it off. And this is a bit more readable. And what do we see? Well, the narrator, since this is a spoken piece, a podcast, is the main person, is the main actor. So that's not super great. This is why I said this works better on sort of formal text where you don't have like somebody saying I a lot and me a lot because those words come up. But the I here indicates that almost everything is centrally tied to the main character. Okay, that makes sense. We get a lot of Ezra, she, pavement. It's an interesting one to have that high. Um, he does get, I think, beat up and thrown onto pavement in this example. Podcast, everything, studio. Kennedy is one of the characters' names, so that's pretty cool. Ezra as well. Willett. So we get a kind of a mix of different things that are useful. It is not useful, right? And then he's. So we have two main characters that are a he and a she. That makes sense. Some other side characters. Kennedy is one of the main characters of Willett and Ezra. So we're getting some useful information. I don't think you'd be able to tell me about the relationships between these characters so much, though. Okay. So let's try that same graph with entities. Okay, now I'm going to have to change my entity plot here because now that I've actually run it correctly. So let's look at what we've got frequency-wise. Ooh, so 10 won't work because 10 is too high. Okay, that would only give me 3. So let's go with 4, 3, 3. Let's start with 3 here. Maybe still a little too low. We'll leave it at 3. But let's same kind of graph. Okay, you will get way less entities than you will dependencies. But dependencies may help you see entities that you're missing, for example. Okay. So we still have I here as our main character. Kennedy again, that's good. Tape. I got it on tape, probably. We got Fisher, a different character. Alan. Okay. So we're getting a little bit better. Okay. I'm still kind of surprised at the lack of full names, but that might be the text that I picked. Let's look if I can see this again. Maybe it's just because of what I picked. I saw a double word. Hold on, where did it go? Maybe I missed it. Nope. So everything that was frequent was single words. Probably the text that I picked. Okay, so what we can see is we get slightly different pictures, but really a same kind of visualization of like, I can tell that this is, without reading it, I mean, I've listened to the podcast, but I can tell that this is a first person point of view because of all the I's, she's, he's, and theys, right? You'll still get a lot of he's and she's in a third person point of view, but you might get more character reference names if it's like more formal text. So this would work better in like textbook or news article kinds of things because they try to use less pronouns so it's clear who they're talking about sometimes if it's good writing. But this is clearly more of a story rather than an exposition kinds of text. And I can at least tell that Kennedy is one of the main characters, and she is. And it's Kennedy Fisher. So our Fisher from our first one, right, wherever that went. Maybe it's in this one. It went away. It was in one of these graphs. But I actually am, oh, here's Fisher. So I'm surprised they're not tied together. So, there's some room for improvement here. All right. Now, all that being said, what can I do to actually get the relationship part of this? Okay, we did all this. Last piece. How do I add labels with Snorkel? Okay. So Snorkel is a cool package because it sort of provides a framework. You still got to do most of the work, unfortunately. So it provides a framework in which you can add labels based on what's in the text. So now that we have the text pre-processed, we could have stopped there and just made graphs, but now that we have this text pre-processed, we could figure out what other features may help us add these labels. Okay. So in text for left to right reading text, right? If you're going to process a different language, so you'd have to think harder about how to do this in, for example, Chinese, either simplified or traditional, Or Arabic, if you're left to, right to left instead. You would change these pieces a little bit. But in, sort of left to right text, where are the clues for the relationship between objects? Okay. Well, in a lot of languages, most of the clues are to the left of the original of the either word. Okay, they're kind of upcoming to the word. So we've got object one and object two. To the left just means it's like right before it. Or even more useful is the words between the two objects. Could we find those words to the right? Yes. So we could do to the left, between, and to the right. It tends to get a little repetitive. So we're just going to do, can I find information I'm interested in to the left of the word that tells me what the relationship is between these two words, to the left of either word, or between them? You could also just stick with between. Okay. So usually these relationships are either before, so this is or to the left, little typo here, or between those words. Now, this is the hard part that I think students and myself have trouble with, is figuring out how you want to label. Like, first of all, what do you want to label? What kind of relationship are you interested in? You might be interested in, like, if you're doing business work, you might be interested in this company is linked to this other company. You might be interested in knowing who sold these companies to each other. You could be interested in competition. Since this is a fiction piece of work, I chose that these two things were interacting. So let me find all of the objects that are interacting with each other, okay? And not just mentioning each other. Okay. This is defined by you. So you have to pick. So once I've had students in different semesters do The Godfather is the one that comes up to me to the top of my brain, where they were looking at whose family. Okay, and if you look at the Snorkel example, it's on spouses, but family could be really interesting. Friends, you could look at relationship, like traditional relationships. And here I'm just trying to see who are the two characters or the two objects that are interacting with each other. Okay. So once you pick a theme, the next component is picking the words that would indicate that theme. Okay, this is the hardest part. After this, you can kind of just change the code to work with your however you want it. Okay? So I've got my character, my theme. Now I need to pick my words for my theme. Okay. If they're interacting, it's gonna be told, tell, telling. I could add another word here. Recording each other, because this is a podcast. They're talking on the phone, they're talking in the studio. So how did I figure these out? I literally opened the text and looked at it. So we have our original tokens, DF dependencies here. We have our tokens. And I just kind of like flipped through and was like, okay, what am I looking for? Okay. And kind of scrolled through it. Okay. This is hand labeling. This is, supervised distant learning. You got to do it yourself so that then later you can hopefully use a machine learning model. So I came up with these words. Now I haven't done any processing on this, no lemmatization, no stemming, nothing. So if you want different word tenses, you should word tense them. So told and tell were two that I need to add both of them. I could do tells and telling because English is a dumb language with verbs as well. Now, then we'll make two little variables here. One that indicates the thing is there, whatever it is, and one that indicates the thing is not there. I have learned this lesson the very hard way, troubleshooting code. I tried to add text labels one time and it just blew up and it took me forever to figure out. So learn from my mistakes. These returns here must be numbers. Don't know why. Maybe someone from Snorkel knows why. And if not, maybe they've updated it, but lessons learned the hard way. Okay. So what do I do with this? All right, there's a couple pieces to Snorkel's pipeline. The first piece is processing functions. So these are functions that's going to take in our data frame in the format we already have it, and it's going to process what it needs for the second function. So this is the first piece in the pipeline. So we've got what are called preprocessors, the processing functions, and then we have labelers. Okay. So what happens is the labeler says, preprocess the text this way, and then I'll label it. Okay, so we're pipeline, preprocessors, labels, output. So these functions allow you to grab those specific tokens. So now hopefully you see the reason that we have a column of tokens, because we don't have to tell the preprocessor to tokenize it. It would be much slower if we had to tokenize it at the same time. Okay? And so this is the function here that grabs the left words. So let's walk through it. So here are all the calls that you have to use to get Snorkel to work properly. Our little preprocessor. Okay. Leave this bad boy alone, essentially. So these are kind of labels that Snorkel tends to use. But canned here is going to be a data frame. That's essentially what we're putting in. Candidate, I think is what it stands for. We're putting in a data frame. Can you change that word? Yes, but I haven't touched it myself. Okay. We can write a window of 5. Now we could put this as part of our parameter. I will tell you a 5-word window is a pretty good one. So it says, okay, where is the end of the word? Okay. So here's our object. I'm sorry, this is end, but it really should be start. Where's the start of the word? That's interesting. I've never noticed this. This comes from Snorkel directly, but where's the word? Okay. Object 1, word ID X. What the heck is that? We've already forgotten. So let's go back. Okay, object 1, word ID X. Spot 0 is where the word starts. Okay. So find where the word starts, and it should have printed out the text here. I don't know why it didn't, but anyway, so find where the word starts. Then this giant thing here, what it does is it says, okay, from the beginning of the text up to where the word starts. Okay, so let's go look at one of these. It's supposed to print one. All right, let's do. Why it didn't print? Probably because I didn't use the word print. Python's so grumpy. All right, here's object 1. All right, so from the beginning to where the word stops, object 1 is me. Okay. It's going to find the word me. It says, okay, from 0 up to 7, but not including it. Going back to the code here. Okay. From 0 up to 7, but not including it. Right. So find where the word starts, take everything before it, everything, whole sentence, and only include the window size. So this is the fancy Python way of saying start from one token back, start from the end, and work your way backwards. So what this will grab is allow 1, Hewood 2, Mr. 3, Tillinghast 4, Godfrey 5. So we'll grab the 5 words before it. Okay. And that is the fancy code that handles that. Okay. Why the -1? Well, we have to do from the end, so that's -1 because it's the last one. Up to, but not including, right? Because of the way Python does sequencing of numbers, what we end up with is the window side here is 5. So what it will do is it'll say -6 through -1. So it's going to count backwards and do -6, -5, -4, -3, -2, up to, but not including. So it won't include -1 because we don't want the word me in there. Okay. So it'll grab everything 0 to me and then work its way backwards. And it does that twice. I don't know. It should be start, really. And what that does is it returns the tokens to the left. Now the same thing here, but the function between 2 objects, this one's a little bit easier to read. We grab the start. Maybe I messed these up. Maybe I got these backwards. This is like weird because the start, oh no, I'm sorry. No, this was correct. I had a brain fart there for a second. So it grabs the first word and it says, what is the second object in that list? Okay. So it says, okay, 7. So it grabs the second object in our tuple. Okay. So the first word ends at 7. Add 1 because we don't need the original word. So start at token 8 and go all the way through where the next word starts. So this one's a little easier, right? Get the word after our first token all the way up to, but not including the word of the next object. If those 2 objects are right next to each other in a sentence, it returns nothing. But otherwise, it returns the pieces between the 2. Okay. All right. And I told it to print. entities down here, but it did not. So I was trying to print this out as we went, but so it'll grab 7 up to, but not including 12. Then we grab some labeling functions. So our first labeling function here, it says the diction. Let me show you the important pieces. So I'm going to flip over here where it's a little easier to read. Okay, the important components. This here is the type of the dictionary that you're interested in. This is where you put in all the words that you want. Okay. And so be sure you change it throughout. Okay. Then, move this over. What is our preprocessing function? Well, this labeling function is for the words between. Okay, so it needs to run the get text between beforehand, or this won't work and it'll blow up. Okay. So use this dictionary as the words I'm looking for, run this preprocessing function, okay. Then return included, which is our 1, if the intersection of those two sets of tokens have my word. Okay. So interaction here is our list of words we're interested in, dot intersection. Okay, intersection takes those two lists. The other list is between tokens, all the words between the two. And it says, do they have a shared set of values? So is there at least one of those words between our list of words we're interested in and our list of words in between? Okay, so do they overlap? Basically, is there any overlap between these two things? So if the length of the overlap is greater than 0, mark a 1. Otherwise, move on. Okay, mark a 0. So this will mark 1 for every time that a word that we're interested in finding is between the two sets of tokens. Okay. Left, a little harder because I've got to do it twice. So it says, is there that intersection between the object 1's left tokens and our word, or object 2's left tokens? So we have to do it once for each to the left, right? Word 1, word 2. Else return not. Okay. So the main key thing here is when you're making these, you can use this code, but let's say you had 2 dictionaries. So let's say you're trying to label it for interactions and for enemies or something. Okay, you'd have to make 4 functions. 1 for the interactions and then a separate one for the entities. So you'd end up having copies of these. So, but just keep between and between together. Okay, left and left together. So if I wanted to do more than one, I could say like talking here. Okay. So you want to call them different names and change the dictionary out. Whew, it's a lot of setup, but once you get the setup done, you can apply those labeling functions to the data frame, and it should have printed little thing. I don't know why it's not printing. That's weird. Anyways, I will fix that. So import the pandas labeling function applier. And put in the labeling functions you're interested in. So I'm going to run left words and the between words. Doesn't really matter what order you run them in. And apply that. Run that bad boy. Okay. So then we take our labels, or I'm sorry, we'll get the labels and we apply it to our dependency data frame. So that's kind of a pipeline that we're setting up here. And remember that this pipeline has 2 other pipelines before it. So this is kind of a long, like pre-processing, labeling functions all together, apply that to a pandas data frame, do it. Kind of a long pipeline. And this is the function that does everything together. It says, okay, I'm gonna pre-process this, I'm gonna grab the tokens in between to the left, and then I'm gonna spit out the output on my data frame. So let's review them. I'm kind of irritated that it didn't print anything. So let me scroll down here. Let's look at what happens here. Okay. And so what we get is left interaction and between interaction, and we just get 0s and 1s. Okay. But we know what 0 and 1 means, so let's put it all together. So we concatenate here. We grab those 2 data frames and just go stick them together. Okay. And then I actually added up left interaction and, oh, good gravy. Here's another typo. So glad I'm finding these typos while we're talking. I tried to add up left interaction and between interaction. Okay. And then filtered the data frame where I only found the ones that had an interaction. Okay, so let's rerun this since that was wrong. So now we have a combination data frame that has, the original to the left and in between, but it says here's anything that has an interaction in it. It's a way to pare down the data. So we went from 15,000 entries to 4,000. It's quite a big filter. From there, though, we would run the exact same code that we did before, right? So to make this picture, it's the same set of code. I'm going to rerun it since it was wrong. I'm going to say, okay, here's my dependencies. They shouldn't be related to each other. And then let me look at this data frame again to see how big our filter should be. So you'll notice that we filtered things down quite a bit. I think 10 probably is actually still useful so that we don't get quite so many bubbles. Maybe 8. Start at 8. Let's look at the picture. Yeah, a little better. So I changed the way that this part works. So let me take that off. Change it back down to 2 because it's a little hard to read. There we go. Now, if I were to compare this to the beginning, what I would see, first of all, I have way less objects to work with, which is good in our example, but now I would see slight differences, right? So I do still see Ezra and Studio, Kennedy's in here, but we do get slightly different pictures. So Ward is one that we didn't have before. Language, so there's a whole bunch of talk in this about they talk in fake H.P. Lovecraft language in this. So it comes up, we get Willet again. So we do see a little bit more of the characters and pieces of the story. So the first one is about the disappearance of Charles Dexter Ward. Cool. Now, I'm going to do the same thing to my entity column, and I'm going to fix my typo. Cool. Let's see here what we need. Yeah. Oh, I called it the same thing twice, which I probably shouldn't do, but that's okay. Oh, I want to create my entities. This one. There we go. So what frequency should I use? Oh, definitely not 10. Let's do 2. Okay, everything that appears more than twice. I did 3 before with my typo. Now 2 might work better. All right, and this time the little numbers, the little lines are useful. Okay. Ooh, I didn't mean to make it bigger. And what do we get? Now we certainly get some of the names actually in here correctly. So Shepley's in here twice, which is okay. Ezra is a character. George Shepley is a different character without running it for you. Kennedy, it's really nice that Kennedy is tied to these because that's the only person that interacts with these folks. Sayers, also a character at the beginning. Kerwin is a character, but she doesn't really interact with them. He's kind of dead. Not a surprise. I'm not spoiling anything. So we get a totally different picture. And that's what's really cool, is that you could use these two together to kind of try to find where the extraction should occur. Okay? Because there's nothing from keeping you from using this labeling data set and combining them together. You could use both for your machine learning algorithm if you were interested. Okay. All right. So I will fix these slides, tell them to print properly, or we're going to view them. So let's wrap all this up together. Okay. So what you've learned across all 3 weeks is a ton of stuff from information extraction. Okay. So what we've covered is key phrase extraction and part of speech tagging. Part of speech tagging using just the nouns in the sentence is another way that we could potentially make some network graphs, right? Just grab all the nouns, grab all the proper nouns, see what happens. Because we know from our previous lecture that part of speech tagging is an easier task in at least English, right? Not all languages have this quite as good, but most of our very popular languages have very good part of speech taggers. Okay, I don't even find it useful to talk about how to train them anymore because they're just the default ones are great. So I could make these co-occurrence graphs between all the nouns in each sentence. So this is another way we could work with the data. We've looked at named entity recognition and talked about how those systems are fairly brittle. Okay, that was last week. And there are ways to improve those systems. I find the way to update spacies is a little overworked, a little complex. And I think that grabbing the information from them using dependency parsing or default NER is a good place to start to see what you might be able to do with it. But there are tutorials online about how to add to spacy system, and they change it so frequently that if I'm making videos a little frustrating on it, but there are a ton of pieces out there. And then we've covered relationship extraction in some fun ways this week, and then how to run all of that together to make these cool knowledge graphs. Because that really is like what's in the data. All of these weeks, one of the big things that we're focused on is like what is in the data. I would like to not read it per, one line by line, but we do need to dig in to make our systems that we're going to implement, however you want to use them for analysis or for production, better by looking at the data and thinking critically about what's in it to improve our systems. So that wraps us up for information extraction, where we put all of this together to make some cool graphs. Thanks for hanging out.